and point out these instruments that we are using to measure the technical properties. Hopefully this works better. And I think you will be doing the experiment you're doing this afternoon is related to those. So it's just to have an idea here what we are measuring. One of these instruments is used for surface interfacial tension. You can see also here where we got the instruments from. But the idea is that you have basically it's a force balance. There is this part here of the instrument that is coming very slowly down. What we have here is a little pot, is a little container that has either a liquid and a free surface, or a liquid and another liquid on top. So we put the this metal plate in the interface, and then it slowly is pulled up. And when this interface breaks, then that's what we record as the force that is related to the surface tension. All this is done automatically in the instrument. This is what is calculated basically. And the instrument calculates from this sigma, which is the surface tension, or if we have two liquids, the interfacial tension. The contact angle, the assumption is that the contact angle here is very good. So the liquid is wetting this plate. This plate is of specific material, so this contact angle is known. So when we do that, we can get these types of curves of surface tension. And this is an example here, just to show you what else we can do. If we have a pure liquid, pure fluid, we will just get one value. Maybe if we change some conditions, the temperature might be slightly different. What I have plotted here is the different values we get if in the liquid we add the surfactants, and this is the concentration of the surfactant in the liquid. And this is just some results we did with two particular types of surfactants. That's the type of curves we get. Surfactants tend to go on the interface. So the more surfactant we have, the lower the surface tension. And this is the comparison. What we also get, we are not going to go into too much about surface tension, surfactants and surface tension phenomena. But what we also have is that when we reach for each surfactant quite high value of the concentration, then as you can see here, the surface tension does not change anymore. And I don't know if people know, how do we call this point here, after which the surface tension doesn't change? Yeah, okay, very good. Yeah, it's critical micellar concentration, CMC. And basically, this means that from that point onwards, we have too many surfactants, and they start forming micelles inside this phase. The phenomena get more tricky, but we can actually get those from these curves. And what I have at the bottom here is an instrument to measure contact angle. Again, it can be done much more simply, but there is anyway an instrument. Cruz is the company that we have it from, which basically means we deposit a drop on a substrate, on a surface, and then from imaging, we can get the, hopefully we'll start again, we can get this angle here, which will be the contact angle of this material, of this drop on the surface. You can do other things as well. I think somebody mentioned heat transfer before, because basically what you see here is evaporation as well. Okay, so if you can also study more complex phenomena such as evaporation, spreading also with these imaging techniques. What you are going to do in the afternoon is that the drop stays as it is, and you just measure the contact angle. As I said, this is the FRIES instrument, but it can be done quite simply as well in a lab. All you need is a good camera, good resolution. Doesn't need to be high speed, because basically it's taking images of the drop and then in some way try to get this contact angle here. So yeah, this is the instruments we use. I will now move to techniques, various methodologies for obtaining parameters in two-phase flows. And I have three main parts here. One is on imaging, and I will discuss it a little bit more. You kind of did some of it yesterday. You did imaging, basically. You had a camera, you had a light. I will then go to talk about a bit more advanced imaging that is based on lasers. And at the end, I will present to you something some people have started doing, and we do in our lab as well, where we're using non-intrusive instruments such as ultrasound probes to get to phase flow parameters. There is a lot of theory behind all those. We can discuss more of that in the outside. And by all means, this is not going to be exhaustive. If people need to use these techniques, they will need to go back to the literature to get some help, okay, some expert to learn how to do more. So this is more of a way of showing you what is possible, but also what is out there in terms of literature and available techniques. So this is basically imaging. Sometimes we call it shadowgraphy because you basically have the light at the back and the camera on the front, or the light on the top and the camera at the bottom. I think you did it like that. And in a way, you are seeing the shadows. It's using any light, LED light, to actually illuminate the channels. That's the setup you had yesterday. You can do it with gas liquid, with liquid systems. You can do it with all types of phases. This microchannel I'm showing you here is slightly different to the T-junction you had yesterday. We have a co-flow configuration. And you see some results here. And yeah, some details on the geometry of this channel. It's a commercial one, and it's not entirely spherical, circular when you go to the main section. Yeah, there will be some images, so if people want to come closer, that's okay. What I show you here, we'll talk about drops tomorrow more, but I just want to show you that by doing this, you can do it even manually, having good images, even manually. With a simpler software in the computer, you can get the drop size. And then, of course, you can build figures like this. What we have done here is, again, we're working a lot with surfactants. We try to see what's the drop size if we change the average drop size, if we change the surfactant concentration. What I wanted to mention here as well is that there is, and again, if you are into this area, it's worth digging. There is, sometimes the images are not as good as this. And a lot of people are working on using machine learning tools to enhance the image quality. We've done a little bit of that as well. We've published something, but there are these capabilities out there. But the first easier thing is you start simply, you get your images, you try to do them as good as possible. So all these things need a lot of care and attention. Been in the lab myself and Professor Ghosh a long time. You cannot just, you need to pay a little bit of attention to have how the light falls. You need to play, to be quite meticulous about this thing to get the good quality images. But it's kind of easy, it's easy to get them. And of course, the camera plays a role. High-speed cameras are good for moving phenomena. We don't have to go to extremes. You need to have enough speed that is faster than your phenomena. Okay, you don't have to have the super high-speed camera to capture a very slow flow. I've seen good images even with mobile phones, if it's slow enough. So yeah, it's you don't need to, if you have a very good camera, well done. If not, it's still possible. I'll say a little bit more on this imaging, and I'm just changing the geometry to show you something slightly different in terms of processing. So, okay, basically we are using a new type of intensified flow where we don't have these T-junctions or the co-flow configurations we had before. We now use two side streams that have, because these channels are small, they have quite high speed. So when they join in this main channel, they create dispersions. I have a photograph in a minute. We call them impinging jets. So it's this idea of the large-scale impinging jets. They collide with quite high inertia, and they form small drops. And this is one of the things we have been using to increase the throughput. We discussed a bit scale out yesterday, very briefly. We'll discuss that more in Thursday. But one way we're doing it is just trying to get as much throughput in the small channels before we replicate, before we multiply them. So we call that impinging jets. And because we have the channel, the jets don't collide in the open air. There's a lot of literature on collision of jets in fluid mechanics. These ones are confined. And William the student did a very fancy drawing here of a schematic of the setup, but basically we have the pumps, we have fluids, and that's where they join. We have the light, we have the camera. Previously, just before, Professor Ghosh mentioned different fluid properties. And it's quite nice that glycerol water mixtures were mentioned. Of course, by adding glycerol in water, you change the viscosity mainly, a little bit the density as well. One thing we play a lot with glycerol in water is because we can match the refractive index, or we can bring closer the refractive index of the aqueous phase to the organic phase. In a minute, I will say why this is even more important when we use lasers. But actually, if you have, and let me go now to the next slide. This is the type of, let's say, dispersions you get in these impinging jets. So the two, can I get the, yeah, the two fluids come with speed, and then the dispersions go down this way. So you might, if you have worked with large scale flows, or if you have done any classes courses, you will know that once you have dispersed flows and the dispersed phase becomes more than about 5% volume fraction, then your images are not good. You cannot see through, because then there is a lot of light reflections, refractions, the images are not good. So one way to try to eliminate this a little bit is to bring the refractive index, the two phases, the dispersed and the continuous, a bit closer. You don't want to completely match, because then you will not see anything. If the two phases have exactly the same refractive index, you will not see the interfaces. But the more close you bring it, the better. So that's why in this case, we tried to not absolutely, slightly match or bring closer that's why we added glycerol in water to bring the refractive index a bit closer to that of kerosene. Anyway, this is the type of images we get. And these are not as clear now. But what I wanted to show you here is that you can do some post-processing to actually get information even from these images. Again, here the maximum we could go was about 10%. Then the images were not easy to see. Okay, so we have all these images, and then this was done in MATLAB actually, and we have published and worked on this. I think I have the reference in subsequent slide. But basically, you can put some threshold. There is this erosion technique to make the circles a bit more clear, the boundaries. Okay, reject features, something that is not very clear. And then there is this, let's say, in MATLAB, there is this option to allocate circles in the objects that you see there, assuming they are spherical. And what the student had done in this case, actually, is that he tried to separate the drops in categories in small, medium, and large. Okay, so with this post-processing, we were able to get decent drop size distributions without doing it manually, because it's always one option to do it by hand. But if you do it a little bit more automated, then you can get a lot of drops. So it shows here that, well, he actually measured between 2,000 and 10,000 drops in each case, which by hand would take long. And we just decided by plotting the mean average diameter over the number of droplets, we could see that, okay, depending on the case, maybe you need at least, this is 200-300 drops to have a good statistically believable result. some drop size distributions. And this is good because we can actually process the data a bit faster. You get the images quite fast, and then you have to spend lots of time to actually process them. So here is for different, this is the frequency, let's say, of the droplet diameter. And we have the dispersed phase fraction is, as you can see, quite small. Here, I'll talk about that. So it's less than 10%. And we increase the velocity, the total velocity. And as you can see, as we increase the velocity from pink to blue, we get a lot more smaller droplets and we lose the larger ones. So that guides us on how to design these impinging jets. And the distributions, that's why we like this approach, and the distributions are quite narrow. And then what we see is that when we change the volume fraction a lot, then we have, it was mentioned before, phase inversion. So this does not mean we have dispersed phase fraction 90%. It means that now the other phase is continuous. And what we found is that in this case, the water is the dispersed phase. In this case, the oil is the dispersed phase. And we saw that the water as dispersed phase has larger, gives us larger drops. And go on investigating why that happens. Now, this was about imaging. There is a lot about imaging because actually it is an easy way that allows you to get a lot of information. The other technique, we've been working a lot with that in the lab. There is also quite a lot of work in the literature, is to not just use light, but to use laser, light. So laser is a different type of light. What laser allows us to do is to two things, is that we can do, as I will mention in a minute, other types of measurements. We can get velocity profiles as well of the phases, not just the shape of the interface, but it can also allow us to get much more clear images, even when we just want to do imaging to see where the interfaces are. There is a lot of work on these laser, let's say, based fluid flow measurements. When we are in large scale systems, okay, even larger than that, we use the laser as a plane. The laser can give a nice plane, and the plane is where we are focusing. So we know where we are in our channel, for example. When we are in macro channels, this is exaggerated. The actual test section is, you saw a big one yesterday. You saw a 2 millimeter. I don't know how low you went in your diameters, but it can be less than a millimeter, 500 microns. In this case, it's we cannot, the laser cannot produce this very thin plane. So what does the laser do is provide a volume, what we call a volume illumination. It illuminates the whole, if I show it here, the whole channel, yeah, all of it. So then we depend on the camera to give us the plane where it's focusing. So where we are inside the channel in the cross section, it does not depend. If I go back here, you illuminate the whole thing. You illuminate here everything. So the camera will tell you whether you are focusing here, here, here at different depths. Let's say the camera is here and you see. In larger channels, if that is a few 10 millimeters or more, the laser itself will create a plane this way or this way. So the camera just sees the plane of the laser. So this is the difference when we do lasers in small channels compared to large ones. So everything I'll show you here is volume illumination. Okay, we have the laser. Now, a few things. So we use the laser because it can actually, we can use fluorescent particles or dyes to help us see better what happens in the flow. It is important in this case to match the refractive index between the two phases. That's why it is quite nice to do it in liquid-liquid systems. We can play with the fluid properties. Gas-liquid systems, it's kind of very difficult to match the refractive index. But because we can do that in liquid-liquid, we have been working a lot with that in the lab. Okay, this also brings the limitations. It means that you can use it to study fundamentals, but it's a lot more difficult if you want to use it in any other system. While, of course, imaging can be used in any system, as we saw before. You don't have to worry what's the aqueous, what's the organic phase. Here we have to match the refractive index, which limits in a way the fluids we can use. Okay, bear that in mind. All the techniques, and that's something to say from the start, there is no best. Each one offers a certain type of information, and I'll discuss that later on, is that they cannot even give you slightly different information if you combine techniques, because their principles of operation are different. It doesn't mean they are wrong. Okay. So let's go and see some measurements now. Right. So the first thing we can do is just imaging. We said that before, that with imaging, with just imaging, you may have blurred. If I go back here, actually, this is a good image. I shouldn't have used it. You may have quite blurred photographs. If that was a plug flow, it would have been quite difficult. You see, there is a lot of shadows to see the film thickness and so on. So what we do now is that we match the refractive index of the two phases. So if we did not, and we add fluorescent dye in one of the phases. Here is the drop formation sequence. Without the dye, we wouldn't be able to see anything, because the two phases have matched refractive index. And this is absolutely true. I mean, you go there and you see where is the interface. There is no interface. First, they're matched. The light just goes through. So what we do is that we add dye in one phase, and this is nice because it is, the dye is all contained within the drop. So it actually is very easy. It's much more easy to get better, let's say, measurements. If there was a film thickness here, even if that was closer to the wall, we would be able to pick it up. It would have been very difficult with imaging. So we'll talk more about drops tomorrow. I just wanted to show you that you can get, for example, here the various regimes of drop formation, and you can even in one particular, let's say, in the dripping stage or the squeezing, you can get the expansion, the necking, and the pinch-off stages. So this is just a dye. Right. Right. And now we can do something similar to get velocity profiles. Again, we have to match a refractive index. Again, we are putting something fluorescent in the flow. In this case, we don't put dye. We put, I hope you can see it, that's why I wanted the lights a bit dimmed. We put fluorescent particles in the flow. Yeah. Okay, let's first talk about the PIV, and then we can discuss this, let's say, different requirements. Do people know what particle image velocimetry is, what PIV is? Who doesn't know at all? And there's no shame to admit it. Have people heard that before? Particle image velocimetry. Yeah. Do you know how it works? No. Okay. So this is very brief, and I will do it by hand, let's say. So in particle image velocimetry, what we do is that we put seeding particles in one fluid. And we get images in a quick succession. So if the flow, I'm saying, I'll try to do this here. I don't know if that appears. Yeah, I'll do it on this side. Okay, so the flow moves forward. We take let's take an interface, and we see the particles. Yeah, we'll discuss a bit. It's a bit hazy, but you actually see the particles. These bright spots is particles. Particles are here. Okay, let's go here, and then in quick succession, we take another image for the instrument. The camera takes another image where the particles have moved here. Okay, and the interface in this case. So then there is an algorithm within the software that what it does is that it cross-correlates the positions of the particles. So it knows that this particle here went here, And because we know the time is different, the frame rate of the camera, let's say, then, and we know the distance, then we can calculate the velocity. Okay, this is a very rough way of explaining PIV, but this is the idea where it's based on. There are variations. If you don't have enough particles, then you trace individual particles, and that's called particle tracking. Because in actual PIV, you don't try to see the actual particles, you get grayscales. So the algorithm doesn't look at specific particles, it looks at the grayscale of the image and how that translates to the next one. Okay, and you can, this is not, I think this one is this one. You can then, by getting these two frames, get information on velocity profiles. Okay, that's why it's called particle image velocimetry. We measure velocities. Again, it is a technique that has been developed a lot, and there are various variations. I'll mention a few here. There is a lot of references as well. As I said, the standard one is more easy to pick up. Then there are various evolutions. In the standard PIV, the micro PIV differs from the PIV in terms of illumination, as I mentioned to you. In the standard PIV, we have a plain laser in large scale systems. In micro PIV, we have this volume illumination. So in the PIV, let's say the classical PIV, what we do is that we have a pulse, a laser that gives two pulses, very close to each other, very short, with a very short time difference, very short. So, but the camera has two frames. Okay, so the camera is not very fast, but it's called straddling camera and can have two frames that are here, and then the next one comes here, further down. And this is a long time. This is time. So the laser, and so these two frames are quite close to each other, and the laser is synchronized, is controlled in a way that it gives one pulse here and the other pulse here. So you have two, if you had the two pulses in the same frame, then you will not be able to see the difference. So it's important to have them in different frames. But this is a very specific particular camera. It's called straddling camera and has this feature that you have the two frames very close to each other. The repetition is quite slow. I think it's like 7 or 15 hertz, very slow. But what is important is that this here is quite short. So the particles, you are able to correlate the particles. If this distance goes very high, the particles from here will have gone somewhere else. It will be difficult to do the correlation. Okay, so this is one way to do that. Another way is to have a continuous laser, so you illuminate all the time, but then the camera is very fast. Okay, so basically the illumination is there, but the camera takes one image now and another image in a short time and so on. However, even that, so that depends on how fast is your phenomena. What we found out is that when we have phenomena where we have a breakage of generation of interfaces, like the breakage of the meniscus here for the drops in the channel, or when you have coalescence, the points where the breakage or the coalescence happens are very, very fast. So in that case, we found that we actually used a high-speed laser instead of a high-speed camera to capture this very fast phenomena. Even a high-speed camera, one of the problems of the high-speed camera is that even though you have a lot of frames, each frame, because they stay open for a very short time, the illumination you get from the laser is not enough to actually see the image very well. That's a problem. So you do need a very strong illumination. Continuous laser cannot provide that. That's why the pulse laser, the high-speed laser can actually do it. And also with the high-speed cameras, sometimes even that speed, the difference between the frames may not be high enough to capture this very last few. This can be milliseconds or even less that this breakage of coalescence happens. So as I said, this becomes more expensive and more tricky. But if your phenomena are slower, like observing slug flows inside the channel, this first approach has been used a lot, has provided a lot of information. So just to show you some now results from that, it's not, I'm not concentrating on physics in this lecture. It's more about on the physical phenomena. It's more about the techniques, but it can actually give you a lot of interesting information. So here we have again the droplet generation. And in that case, what we have done is we used different surfactant concentrations, and it's no surfactant, a little bit of surfactant, very high concentration of surfactant. We're above CMC. And what you get here is, it's quite interesting how the velocity fields inside the drops change. Here, what you get as the drop forms is you get this recirculation. Once you start forming the surfactant is a little bit higher, you still see it maybe not as much. But what is interesting here is that once you have a high surfactant concentration, this thing behaves like a solid body now. It just moves forward. And this is because you have a lot of surfactants on the surface, which here the surface is more mobile, and as it moves, it allows the circulation patterns to form. Here, it's not possible anymore. So this is very important if we want to try where the surfactants go, or how do they affect the droplet generation. And of course, if you are trying at the same time to do CFD, computational fluid dynamics modeling, it's very good for doing the comparisons. Yeah, okay, mentioning about comparisons, this is some CFD results. And that's the difference, let's say, of techniques is applying all these techniques on the droplet formation. This is the imaging, this is the PAV results, and you can see how the surfactant concentration, this is C over CMC, affect these profiles, not just while you're developing the drop, but also when it's actually formed. And I'll show that here, but we're not talking about CFD, just that you get what you get from the experiments. In that case, the CFD helped us to understand where the surfactant is actually, because it's very difficult to get that from experiments. If you confirm that your simulations are good, then you can go beyond. And I don't know if that I have it here or tomorrow. Okay, it's in tomorrow's lecture. But basically, once we trust our CFD, we can go and say, okay, because with CFD, you can do the surfactant concentration. You can see where exactly it is. And then you can relate the surfactant concentration to the velocity profiles. I will, okay, this is a fancy technique. We used it in the past. We didn't do anymore. But other people have developed as well. I just thought we'll add it here because it just shows capabilities. If you start working with this area, it might be worth to explore a few cases to see what is possible out there. So in this case, what we did is that we had our laser, and the laser actually provided one light. But then this is often PAV, macro PAV happens in this setup. I don't know if people have used it at all, but you might have an inverted microscope. You put your microchip here. You might have an optical piece to see what's going on. That basically the light comes here and comes out on this side to go to the camera. So in that case, and here is our setup. In that case, what we had is that we introduced a combined light here, but then and we seeded our two faces with different particles. So in the previous example I showed you, we only had particles in the water phase. Now we tried to put some different particles in the organic phase that had a different emission light emission spectrum. So basically what you get in this case is the emitted light. Okay, so maybe I should have mentioned that before. When we do PAV, we have one light that is sent to the setup. It's usually a green light. But what is the particles emit is a different wavelength. Okay, I'll mention it here because this is quite important. The wavelength is different. because the camera will have a filter here, completely block all the green light and only receive the emitted light, which is usually something slightly higher. The reason for that is that because we have the small channels that have a lot of material, solids, a lot of interfaces, if we just used the same light, we wouldn't be able to see anything. So in a way, we block all these reflections from the walls of the channel, inside, outside, everywhere, by only reading, putting a filter to avoid the green light and only reading the fluorescent lights. Okay, I should have mentioned it, but it is an important thing in microchannels, and that's why we use fluorescent particles. And we do that here, but as I said, we use two different types of particles, and in this beam splitter, we actually split the two wavelengths. So we have one camera receiving the aqueous phase particles light and the other the organic phase particles light, and that's one result we can get. If we do this, we can get the flow velocities, not just on the dispersed phase, but on the continuous phase as well. And what we get here, this is just one case for a system without a surfactant. You see all the stages. You have the drop forming, expanding. Here is expansion this way, radial as well. Here it keeps moving on the front axial. We see the neck forming and what happens to the outside flow when the neck forms. And then finally the drop detaches. And as it detaches, the interface goes a little bit back. And this is what creates the circulation zones we saw before inside the droplets. And the thing is repeated. Okay, so this is about imaging techniques. Looking at the time as well. Before I move on, is there any questions? I know it was quite fast, and there are several details that we did not cover, but I just wanted to give a flavor of what is possible and what sort of phenomena you can capture with imaging, the different types of imaging. Happy to discuss that later as well. But one last thing I want to mention, the last technique I want to cover is this ultrasound measurements. Maybe I'll go like this. So imaging is marvelous, but of course, it is quite limited in a way. It's very good for the lab, it's very flexible, but you do need to have transparent test sections, transparent fluids, and basically to be able to see. So what we have been trying, and a number of other people have been trying to do, is to find other non-intrusive techniques that may not depend on the transparency of the materials. And just because we had the opportunity, we started working with ultrasound. Sound is quite marvelous. You can use it, you don't need to see, you don't need to have transparent materials. And the three types of measurements we concentrated were the overall volume fraction, the size distribution, and quite ambitiously, but we're still working on that, velocity profiles on dispersed systems. Use of ultrasound, sound is not new. Yeah, you might know that the Doppler effect, people have used that in large volumes, let's say, to get velocities. So the ultrasound is used a lot to pick up defects in solids. So it is in fluids is not used as much, but perhaps there is something there for ultrasound as well. The good thing is that it's not as expensive. It is and does not depend on transparent materials. And it's a lot more, it's safe to use. With lasers, at the moment in the lab, we actually have to, to take so many precautions, while with ultrasound, it's so much easier. The difficult bit is that the post-processing is more difficult, has a lot more steps, depending on the measurement that you want to do. So just one example here, and then I will start with the easier measurement. It's quite straightforward as well, is the volume fraction. This is not exactly a microchannel, but because we have stratified flow, but it's flow, it's a clear flow. This is all water stratified flow. And we can also see the interface. So what we have here is that we have the ultrasound set up. We send a wave and we receive it here. And in an oscilloscope, we can see the wave we are receiving. And you get something like this. So this signal, in this case, is quite easy to interpret because the sound will go here, will reflect itself on the walls of the channel, will go through, will will reflect here, let's say, because we have the interface, and then the same with the opposite wall. So we know we are on one wall. This is the oil phase. This is the interface. This is the other phase. So we know speed of sound. We have to measure the speed of sound, or we can find it in literature in oil and water. Everything is recorded in time. So knowing the speed of sound and the time, we can get the this distance. Okay. Why is that important? If we didn't see the flow, we may not know, we wouldn't know where is the interface. Yeah, we just discussed before that we have in situ volume fraction and input volume fraction. This is a very common phenomenon in multiphase flows. The volume fractions you put in the inlet are not the same in most of the cases to the volume fractions you have within your channel. So it is very, very important to get this local in situ volume fraction. And this is an easy system to understand the sound, the behavior of the ultrasound. So, and if we had a steel pipe, for example, common in industry, we wouldn't be able to see it. Now we can see it and we can verify it. Okay, so we actually did a comparison between ultrasound and of the height and the imaging, and yeah, the results are good. So I will see what's the next one. Yeah, so I will. This is an easy example. This is to get the height, but we can also get the volume fraction. I will not go with too much detail into this, just to give you how it works. And there is a lot more details in the literature. The speed of sound in a medium depends on the density mainly of the medium and this acoustic impedance. But it's kind of varying linearly. So if we have one fluid, we can measure the speed of the time of light, how long does it take to go through. And if we know the size of the channel, we can get the speed of sound in that medium. If we now fill the channel with a different fluid, we measure the time of light, how long does it take to go through, using things like that. And if we know the diameter, we get the speed of sound in the other medium. Now, if we have mixtures of the two fluids, the speed of sound to go through the mixture, it depends on the percentage of each fluid. And there are two ways to do it. We can do some calibration of the instruments outside, and we say, okay, let's put 10% water, 20, 30, etc. What is the speed of sound? And we then do a calibration curve. So for or the time of light for different percentages of oil. So here, 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 and this is your calibration curve. We can then put it in an unknown mixture, and we can see from the time of light what is the percentage of oil. We can also do it mathematically, and that's what I'm showing to you here, because the correlation is linear. The speed of sound in each of the medium varies. The speed of sound overall depends on the percentage linearly of each part of the fluids. So we can use that, and that's what we have done. Not just in this case we get height of interface, but in more complex systems like dispersions. This is dispersion we saw before with impinging jets. We can get the volume fraction. Okay, so this is two different examples. This is from the the small impinging jets I had before. This is the size here is 2 millimeters. So we had the volume fraction okay, and the sound speed, okay, this is this graph, but we compared the volume fraction with the images at low concentrations, and we were okay. The good thing with ultrasound is that we can go beyond this 10% that the imaging allowed us. With imaging, we could only do up to 10%. With ultrasound, we have shown that we can go to quite high percentages of the dispersed phase. And in this case here, this is actually a stirred vessel. I'm only showing you a part, but we try to do imaging, fluorescent imaging as well, and we compare the volume fractions with the imaging and the ultrasound. And so this is the imaging, this is ultrasound, and we were quite good in agreement. So this is one way and one easy experiment in a way to do to get volume fractions, especially if your flow patterns are dispersed or anything else. We talked about annular flow, dispersed flow, plug flow, and to get it without actually seeing what's in there. The next one, again, I'm not going to go a lot into the theory. This is based on the Doppler effect. This is something we are trying to get to do better now. But again, the same channel we had before with the impinging jets. We now have the two sensors, one the transmitter and one receiver on the opposite side. And we can here we combine two things, two pieces of information. When you do it in big volumes, you usually depend on the dirt that might exist inside your fluid. So you transmit the sound, the ultrasound, it hits this moving object. Because of the velocity difference, there would be a shift in the ultrasound frequency, and you pick up a different frequency, and this shift change in frequency gives you the velocity of the moving object. So what we do now, when we use our tracers are the drops. When we put the ultrasound through, the ultrasound will hit each one of them. So we read the signal that has a lot of shifts, let's say, because these drops may be moving at different velocities. And we also know the distance because we have the signal we had before that shows us how far inside the channel, at which distance the wave has gone. So we know to associate one shift in frequency with one distance inside here. And from that, we can get velocity profiles like this. We are in the process of validating it. There is a bit of post-processing. What we found out is it is important to have the sensor with some inclination, because in that case, you can also get the direction of the flow. If it moves forward or if it moves backwards. But a lot of this also, I mean, every technique, as I said, has its own limitations. Ultrasound, the problem with ultrasound is that you might have attenuation. So you really need to consider let's say, the strength of the signal and the frequency. Higher frequencies are getting attenuate more than lower frequencies. So this is how to design your system. But you can get velocity profiles, and we have used that to get actually velocity profiles in solid particle particle fluid flows in fluidized beds, where it's very difficult. I mean, you need very expensive techniques to get any information about the particles in fluid bed systems. The last one now is the drop size distribution. And this is something that we think we get good results. It's more involved technique. It does need, you always need to bear in mind, again, what you're measuring and what you're getting. But it is very good, especially when we have to deal with very dense suspensions. As we said, you can only do up to 10% with imaging or even less. We believe we can go higher with this one. So I'll explain again the technique. I won't go to too many details because it is quite involved. There is a lot of post-processing. So if somebody wants to really start working with the techniques, there is a bit of reading to do before that. But I will give you the main idea of what happens. If we have a dispersion like this, we can have the sound wave sent to the dispersion. each of these drops will scatter the sound, the ultrasound. So the intensity of the signal will diminish, will attenuate. So this attenuation depends on the size of the particle and the wavelength of the frequency of the ultrasound. So the and also the particles have to be comparable. The wave frequency has to be, or wavelength has to be comparable to the size of the particle. Because if the wavelength is much bigger, the particle doesn't really affect it. If it's much smaller, again, we're not going to, it's all going to be scattered. So if we have a size distribution, we need to have different frequencies of ultrasound to capture different particle sizes, drop sizes. So what we do then to prepare for this measurement is that we send ultrasound different frequencies inside our sample, and we read this attenuation. How much it is, attenuation coefficient is how much is the signal received, the intensity, without any inclusions in water, for example, and how much is the intensity if we have some inclusions. Okay, this reduction in intensity is what we call attenuation. So I will go here, and as I said, just to try to understand the main idea, and the maths is in the paper. So for the attenuation, this attenuation will depend on the drop size distribution or the particle size distribution, and also on some correlation, okay, that relates the wavelength with the particle size. So if we know if we have all the information about the frequency, the particle size, the properties of the fluids, we can actually calculate the attenuation. Yeah, if we know the drop size distribution, if we know the properties of the fluids and the frequencies, we can calculate the attenuation. What we want is to do the inverse of this. We want to measure the attenuation to get the drop size distribution. Okay, so it's like an inverse problem mathematically. And these are capital because you deal with matrices. It's many frequencies and, many frequencies of the ultrasound to get the drop distribution. So basically, the forward problem, let's say it's easy if you know the properties. What we want is the opposite, because the inverse, because we measure this attenuation and we need to know this one. And this is the whole idea, and that's why I'm saying this, have a look, is physics about sound and interaction with particles, but it's out there, it's known, it can be found. So that's why we measure the attenuation on various frequencies. So we have this here, and we try to calculate this. And mathematically, you need, once you do this inversion, to do some smoothing, just to make this to work, to be solved mathematically. So basically, that's how it works. That's the experiment we do. The experiment we do is that you put a lot of frequencies and you read the attenuation. The other thing we need to do is a little bit of trial and error. If you don't have any information about your system, you might need to try different frequencies because, as I said, to capture smaller particles, you have to have higher frequencies. Going this way. Smaller particles, higher frequencies, because this is the one that have the smallest wavelengths. Okay, so you might need to play around. If you're stuck because you can only have a certain frequency, then of course that limits the smallest particle you can reach. With all techniques, we have to have all these things in mind. Even with imaging, we can't capture absolutely everything. Your resolution of your camera will tell you what's the smallest particle you can detect, or drop size. So it's every technique has its own pros and cons. Worth thinking about it before you. It's not, even imaging is not the absolute truth. You have to think what you're measuring. How do you measure it? Okay, so I want to show you some results on that because we have spent a lot of time trying to do it. And so these are three different examples. This is our impinging jets I had before. This is now a pipe flow. This is a centimeter type flow. And we have silicone oil dispersed in water. Here we had kerosene dispersed in glycerol water because we try to have a little bit better imaging, and we try to bring this to refractive indexes closer. And this is silicone oil dispersed in glycerol water. This is a stirred vessel. And you can see here what is the comparison between imaging, in this case, imaging and LIF. There are differences, and we can talk about the differences. They are discussed in this paper. Actually, we discussed this case here, what you can get. And the discussion is interesting. As I said, nothing is absolutely correct. There is a reason why you can only measure so many things with the LIF, for example, or with the ultrasound. So the good thing with ultrasound, I think this is one more very quickly. The good thing with ultrasound is that if you think, and this is my interest on that, is that it is an instrument that is easy to use even in non-transparent environments. It can give you online information. So if we are thinking about what people have been talking about, digitalization of processes, what you need there is online sensors to read quickly what you have in your system. You cannot do PIV in a plant. Okay, you do it in the lab. But if you want to have this quick information, then you need instruments like ultrasound, pressure transducers to the same job, thermocouples, because you can connect them online, you can read information straight away. And that's why it has some use in that case. My last slide is pushing a little bit the techniques. So this is more for the lab to get more information. What we have seen so far is measurements of hydrodynamic properties. We tried at some point to see if we can use laser-induced fluorescent imaging to see concentration gradients, to measure concentration. The reason we decided to do that is because we were doing some extraction of lanthanides, of europium. Europium is a lanthanide, it's used a lot, it's one of the critical metals. In that case, it was nuclear related, because it's also one of the things that are in the spent nuclear fuel. But what we did was basically extraction of europium. Europium is a lanthanide, so it fluoresces, which is marvelous. Because it means that while the extraction is happening, if we have laser light, that's how we thought, we could actually see where the europium is. Has it moved from the plug to the slag? How much of it? That was our setup. What I have here is the fluids. And in that case, we actually used ionic liquid because we were working a lot with ionic liquids. But of course, you could use kerosene. And the extractant in this case is the CMPO that has this long name that I have down here. Why we did the extraction this way is a mass transfer problem. We can discuss it. It's not related to the techniques, but that's the fluids we had. Our setup, that's a microchip we used. That's all bought, dolomite. And that's the setup. We had the camera, we had the laser, continuous laser in this case, and the T-junction was here. So we were measuring somewhere down here. So there was, again, quite a bit of post-processing, because there are always issues that would appear with these techniques. What we found, for example, is that our ionic liquid was very bright. And that meant that the light emitted from the ionic liquid and the europium that was ending up in it was actually distorting, let's say, the light that we had in the other phase. So we had to do some background deduction, subtraction, and so on. It was not easy, but the results are interesting, and they can again be combined with the CFT. So what we have here is that we have our europium in the beginning in the aqueous phase, which is the slag, and we wanted it to go to the plug phase, which is the ionic liquid. And what because the measurements, we cannot move our camera. So we were always measuring at one fixed location. So what I'm showing you here is the effect of velocity. So if the velocity of the flow is slower, at this location here, only a certain amount has extracted. If it's fast, if the velocity is slow, there would be more extraction happening. If the velocity is fast, not much extraction would have happened. And that's what you see here. Slow velocity, as you can see, there is quite a bit. That's the europium in the aqueous phase, and that's in the lag flow, in the ionic liquid. Some has extracted. As the velocity increases, as you can see, a lot less extracts. And this is interesting because it doesn't just give you, you can give you the average concentration, but it also can start giving you patterns of how this extraction happens. As you can see, seems to be certain circulation. Why is it all on the bottom and on the top? It depends on how the fluids join. So they can be discussed. So basically, you can start analyzing not just average concentrations, but also the concentration profiles. How does extraction actually happen? Where the mass transfer comes mainly from. So I will stop here. This is an interesting way. It was not easy. But again, it does provide additional information beyond just velocities and flow patterns. So that's me. Stop here.